All right, so we're going to start talking about some different operations with vectors now. So the first thing is scalar multiplication. So notice this first expression says 3v. So that means 3 times vector v. So imagine like vector v being tripled. So what happens is you have result in a vector that's 3 times as long as v and in the same direction. So if this down here is a picture of v, 3v would be, so I did this to show you each piece, but really the vector itself would be this whole thing, just one big vector. All right? So the same is true of fractions. 1/2 v would be half as long. The negative actually makes it go the opposite direction. So negative 1/2 v results in a vector half as long as v and in the opposite direction. Right? So it would be, it would start here and it'd go the other direction, but it would only be half as long. So that'd be negative 1/2 v. So a negative is going to change the direction. Right? I have a picture here of some different scalar multiples. So we have first v, then half of v, and then 2 times v. Notice all those are the same direction, they're all positive. Then we get negative v and that flips around. And then we have negative 3/2 v, which is 1.5 times v, but in the opposite direction of v. All right, so quick recap, 2 vectors are equal if they are equal in both magnitude and distance are the same, magnitude and direction. If c is a vector, then negative c is defined as having the same magnitude but reverse direction. Subtracting c is the same as adding negative c. So typically we talk about adding vectors, not really subtracting vectors, because magnitude and direction, it doesn't make as much sense to subtract, and we'll see about that in a minute. And then multiplying a vector by a number, which we call a scalar, has the effect of changing its length and potentially its direction if it's a negative. All right, when adding 2 vectors together, the sum is called the resultant. All right, so that vocabulary is really important to know and remember. So vector addition geometrically. To add vectors u and v, you're going to place the initial point of v, so that's the second vector, at the terminal point of u, which is the first vector. Once you do that, you're going to draw a vector from the original initial point of u to the new ending point of v. All right, so that probably sounds a little confusing. Look at the first example. It says sketch u plus v. All right, so we're going to focus in on just this first one. So u is the first vector. We're going to add v to it. So that means we're going to take vector v and we're going to put it at the terminal point of u. So I'm going to start here at terminal point of u. I'm going to make a copy of that vector v. So there's v. So then u plus v would be from the origin where u started to the end of where v ended. That would be u plus v. So the pink is our resultant vector. And that would be the answer to something like u plus v. All right, we're going to try another one. Sketch u plus v. You can try it out first. Again, it lists u first. So we're going to go to the end of u and make a copy of v. And then once we have the copy, we're going to draw the resultant from the start of u to the end of where v ended. So there's v, u plus v. And so again, we call this u plus v, this piece, our resultant vector, which is really the solution to adding and subtracting vectors. Notice geometrically, without any marks on the grid, it's hard, and I kind of had to do estimates. So my resultant vector might not be perfect. So we're going to look in just a minute about how we can actually do it more precisely. So in general, like we only added 2 vectors on the previous screen, u plus v. Well, here what you see is we have 5 vectors. So we have a plus b plus c plus d plus e, and that equals this resultant vector r. And so you connect where you originally started with the end of the last vector, and that's your resultant. Notice when we change up how we add things, we still end up with the same resultant vector on these. So I just changed the order of what we're adding together, but I still got the same resultant vector. So remember, we care more about not where it's located, but what are the components of it, and every one of these have the same components. So again, that just goes to show you that even when you're adding vectors, just like when you add numbers, that it's commutative. Like when we add them, it doesn't matter if we change the order, we should still get the same result. All right, so how does this look doing vectors added algebraically? Well, when we have vectors in component form, u is 1, 2, v is 3, 1, to determine u plus v, literally, you're going to add the x components, so 1 plus 3, add the y components, 2 plus 1, and we get a new component vector 4, 3. So this tells me in standard position, go right 4, up 3, and that's going to be my vector. Geometrically, we would start with vector u, which is over 1, up 2. At the end of u, we would put v, which is 3, 1. So I'm going to start at the end of u and go right 3, up 1. I'm going to draw that vector. And then my resultant, or the answer, would be connecting where u started to the end of v. So this is u plus v. And notice I go over 1, 2, 3, 4, which is what I had here. And then up 1, 2, 3, which is what I have here. So my components match with what I have in my picture. All right, stay tuned for some more fun with vectors.